Hi everyone, my name is Neha and this is the 17th lecture on Introduction to Automation. In this lecture, we are going to learn about DC motor control and braking. Let's first see DC motor control for larger motors. For larger motors, say about 20 ampere or more, the hardware needed to supply pure DC, it becomes bulky and expensive. So in that situation, we use silicon controlled rectifier, which is also known as SCR. And this SCR, it provides both rectification and some measure of control. Here you see the symbol of SCR, and this SCR, it is a member of a thyristor family of semiconductor switching device, and it is of a 4-layer, and it has 3 terminals. You can see here, first is the anode, second is the gate terminal, and third is the cathode terminal. And you see here, this is the IA is the anode current, which is flowing from anode to cathode, and this SCR is switched on by applying a low voltage at this gate terminal. This is called your gate terminal, and this VGT is the gate terminal voltage. So from here, typically about 0.6 to 3 volts voltage is sent, and once this voltage is sent, the thyristor is turned on and it stays on even if the gate voltage is removed. Now to turn off the thyristor, this anode current should be less than the threshold current, which is also known as holding current. So when this anode current is less than the holding current, then only the SCR can be turned off. That's the only way to turn off the SCR. And if you see on the right, it is a SCR equivalent circuit, and if you notice, then it looks like a switch. So this SCR here, if you see, it looks like a diode and a switch. So it do both the functions, which means it rectify the signal as well as it works as a electronic switch. Now next we have DC motor control from an AC source using an SCR. So here in this circuit you see a single phase AC voltage is connected, and it is in series with this SCR, and further it is connected to the motor, and then this SCR, its gate terminal is connected to this trigger circuit. From this circuit, some gate voltage is applied to this SCR, and this trigger circuit, it provides 1 pulse for each cycle for the AC. And here you see this diode is connected in parallel with the motor, and this diode is called your freewheeling diode. And this freewheeling diode, the function of this diode is to provide an escape path for the energy stored in the motor winding when the SCR is turned off. So here on the right hand side, if you notice, this top waveform is the AC waveform from a voltage source, and this VM is the voltage across the motor, and this VT is the triggered voltage here. So what will happen? So this is your normal AC signal, which has positive as well as the negative cycle. And what will happen when you trigger the SCR at a particular point? So for example, if the circuit is triggered at this point, then what will happen? The motor will start working from this triggered position, or you can say that your motor will be turned on at this particular point, and then will continue to run in the positive direction. And once it reaches to the negative cycle, the motor will be turned off. Now, so this type of waveform is for long conduction. Why do we say that long conduction? Because if you notice, the trigger has been done in the initial starting of the AC cycle. So which means motor will be on at this particular point, and it will basically rotate for this duration of time, which is longer. Whereas if you notice here, this is the same AC signal, and here you have triggered almost at the end of this positive waveform. So if you trigger at this position, then you see that the conduction time for the motor will be very small. So this is the shorter conduction time, and this is for the longer conduction time. So in conclusion, we can say that the motor voltage, which is Vm, it stays at this 0 volts until the trigger pulse Vt turns on the SCR, and once it is turned on, then the motor voltage it is going to be equal to the AC voltage of the remainder of the positive half of the cycle. And by just controlling the delay time of this trigger pulse, we can control the speed of the motor. So in this one, we just used only one SCR. Now let's see next. So this is a full wave SCR DC motor control circuit using multiple SCRs. Here we have used two SCRs, SCR1, SCR2, and then we have two other diodes, this and the one is this. And then we have a freewheeling diode connected in parallel with the motor. So during the positive half cycle, this SCR1 and this diode, they will conduct. And during the negative half cycle, this SCR2 and this diode will conduct. So the direction of current during the positive half cycle is going to be like this. The current will start flowing from here, turning on this SCR1 and then further turning on the motor and then completing the cycle through this diode, and then from here to till here. Now during the negative half cycle, this will become negative and this will become positive. So current will flow from here, turning on this SCR2 and then turning on the motor and then completing the cycle through this diode and from here till here. So that's how the cycle will be completed in the negative half cycle. Now let's look at this waveform. So we see that VT1 and VT2 are the triggering voltage for these two SCRs, SCR1 and SCR2. And we know that during the positive half cycle, we trigger through this SCR, which is SCR1, and which means the voltage is VT1. So this triggering voltage will be for the positive half cycle, and this SCR2 VT2 voltage is for negative half cycle. So this is the negative half cycle triggering voltage. And then we have this Vm, which is the motor voltage, and this motor voltage waveform has been obtained from these triggering voltages. So let's see if the VT1 is triggered in the positive direction, then what will happen? The motor, it will follow the AC voltage after it got triggered. So that's why you see this curve. And then let's see what will happen. When it reaches to the negative half cycle, it will be turned off. So that's why you see it is turned off. And after some time, this VT2 will be triggered. And once it is triggered, then again your motor voltage will be turned on. So that's why you see this motor voltage is turned on, and so on. So it will continue. You see here, this VT1 will be turned on, and then again VT2 will be turned on. And so all these triggering point, your motor voltage will be turned on. So we see that we got the rectified voltage along with the motor control through these triggering voltages. So now let's see next. Next we have full wave SCR motor control using a full wave bridge. So here you see we have used diodes. 4 diodes has been used, and this diode will provide the rectified voltage, so which is represented by VREC. So you can see this is the AC voltage which is going from here, entering from here, and then we have a rectified voltage which is this. And I hope you know how the positive and the negative half cycle works. So let me tell you quickly. So when this is positive and this is negative, then the direction of the current flow will be from here, turning on this diode and then turning on this SCR, and then this SCR is also triggered through this VT1, and then your motor will be on and the current will flow from this diode and then completes the cycle. And when this is negative and this is positive, which means in the negative half cycle, then what will happen? The current will flow from here, completing the cycle, and then turning on this diode, and then that's how the cycle is completed. Now we know that from this full wave bridge, we will be getting the rectified voltage, which has been shown over here. This is the rectified voltage. Now to control the motor, what we will do, we will put a SCR here. You see this SCR is here, and this SCR will help in controlling the motor. So this through this SCR, a trigger voltage is will be supplied VT1 through some triggering circuit. So whenever this SCR will be triggered, after that point your motor will be turned on. So for example, the VT1 is triggered over here, so you see that the motor is on for this duration, and then it will be off until the next triggering has been done. So in the next triggering, the motor will be turned on again, and then this will be the waveform for the motor. Now if you notice here, we have just used one SCR, and this one SCR is controlling the motor voltage, and along with this diode arrangement we are able to get the rectified voltage. So this is one of the motor control circuit. Now let's see next. Next is breaking the DC motor. So there are some application that requires motor to stop more quickly, and in that case we use one of the method which is called dynamic braking. And in dynamic braking, we use the braking resistance. You can see this braking resistance is placed across the armature, or you can say it is placed across the motor. So what will happen when the supply of this DC motor is disconnected, then this DC motor, it will work as a generator, producing the braking torque. So what will happen, all the current in this motor, it will pass through this braking resistance when the supply mains is disconnected. Then whatever the inertia torque it has, it will pass through this braking resistance. So this braking effect is controlled by varying the resistance connected across the armature. So here the power to heat the resistor is coming from the mechanical inertia of this spinning motor. So more the power used up by this braking resistor, the sooner the motor will come to the stop. So I hope you remember the formula for power dissipation, which means P is equals to I square R, where I is the current and R is the resistance. And that formula indicates that the power is more influenced by a change in current than by a change in the resistance. So thus the braking action, it can be increased by allowing more current through the resistor, which is done by making the resistance of this braking resistance smaller. So smaller the resistance, more current can pass through this resistance, and then sooner your motor will stop. Now next we have another method of breaking the DC motor, which is called plugging. So in this plugging, let's first see the circuit. So this is our motor, and this motor is connected to the field winding, and from here supply is given. And then here, if you notice that the switch is given, two switches are given. If we see this switch can connect to this run position and then to this brake position, and this brake position has this braking resistor over here, and then further connected to a switch, and then we have this another switch here. So this switch can be attached to this terminal and to this terminal. So what will happen, let's say right now our motor is being fed from this direction. Positive voltage is going from here, turning on the motor and then completing the cycle till here. So in case if you want to use the plugging method for breaking the DC motor, then in this method the armature connection or the motor connection, they are reversed. How they are reversed? So this terminal you see here, this will be connected over here, and then this terminal, it will be connected over here. So if this is connected to this terminal and this switch is closed, then which means that this terminal is getting the negative supply voltage, whereas this terminal, when it will be connected to here, this will be getting the positive. So initially it has positive and this is the negative, but after changing the position from these two switches, this will become negative and this will become positive. So one thing you know that the motor when it runs, then it will produce the back EMF which will oppose the direction of the line voltage. So remember that it will have some back EMF which will have the the direction opposite to the line voltage. So what will happen when we reverse the direction of this motor supply, then motor will tend to run in the opposite direction, and due to the reversal of this armature terminals, what will happen, the applied voltage, it will have some applied voltage, that applied voltage plus the back EMF it has previously, they will basically add up, and they will move in the same direction. So hence the total armature voltage it will exceed. So this sudden large voltage, it will cause large inrush current, which could actually damage the armature. So to limit that voltage, or to limit that current flowing in the motor, what we can do, we can use this braking resistance which you see here. This braking resistance help in limiting the current of the motor. And when the motor finally comes to a stop, then the reversing voltage should be switched off, so that the motor doesn't start to run in the backward direction. So this is the way how it works, and this is similar for both the series and shunt wound methods. And this plugging, it gives greater braking torque as compared to the rheostat braking which we saw previously. And this method is generally used in controlling elevators, machine tools, printing presses, etc. And you see here it is the same thing. When the supply main is reversed, then the voltage line line voltage, it will adds up to the counter EMF, and as they both of the same polarity, then what will happen, large inrush current will be produced, and that can damage the armature. So it's the same thing which we have discussed. Now let's see next. Next we have brushless DC motor. So far we have seen the motors with the brushes, and there were some disadvantage by using those motors, and that disadvantage is that those DC motor, they have brushes, they rub against the commutator, and due to which they wear out easily, they get dirty, and they cause dust, and they sometimes cause they sometimes cause noise also. So with the help of this brushless DC motor, it operates without brushes, and in this brushless DC motor, it is more complex compared to the previous one, but the result is a motor that is extremely reliable, very efficient, and easily controllable. So this brushless DC motor, it is these days it is becoming very popular, and particularly in those cases where the motor must be operated from a DC source, such as a battery. So let's see in this picture. In this picture we see this armature, which is that called rotor, and this rotor is a permanent magnet, and it is surrounded by these three field coils. So this A, B and C are field coils, and you can see that in this the north pole of this rotor magnet is attracted to the field coil, and this is the south pole of the field coil, and this is the north pole of the field coil. So as you know, north and south, they attract, so you can see that this rotor is right now in this particular position. And also notice that right now at this particular position, this A field coil is connected to the supply. So you can see that the switch is closed here, so which means this coil will have some current due to this supply, and that's why it is creating this magnetic field, and that's why this rotor is in this direction, closer to this field winding. And while at this particular time, this coil B and C field coils, their switches are disconnected, which means they do not have the supply current, and that's why they don't have the magnetic field across around this. So once it rotates here, then what will happen, this field winding will be turned on, so this switch will be closed, and then this will create some magnetic field, so then rotor will move towards here, and then this will be turned off in that case, which means this switch will be open, and this switch will be closed, and this switch will be open. And then in the next cycle, what will happen, this will be open, this will be open, and this switch will be closed, and this will create some magnetic field, and then rotor will be attracted to this field coil. So that's how it goes on. And if you have multiple field coils, then this rotor will rotate very fast. Now if you see on the right hand side, we have some sensors here connected, and in this this sensor system is used to direct the switching from one field to another with the help of any sensors you can use. For example, you can use Hall effect sensor, which can help in determining which field coil you want to turn on. So here we are using optical slotted coupler, which is a position sensor, and it is used to control the field windings. And then you see here we have this rotating shutter here. When the shutter is open for sensor P1, then what will happen? Coil A, or we can say field coil A, which is this one, it will be energized. So you see that this is connected to this field coil A. So this field coil A, it will be energized, and when the rotor actually gets to field coil A, then sensor P1, it will be turned off. And then what will happen? Sensor P2, it will be turned on, and it will energize the field coil C. Here you see it is connected here, field coil C to sensor P2, and P3 will further turned on, and it will energize coil B. So this process will continue, and in this manner this rotor, it will rotate with no electrical connection between the rotor and the field winding. So that's how this brushless DC motor works. So this is the end of the lecture. Thank you so much for watching.